So direction is very important, and magnetic field is a vector quantity. That is why we use crosses and dots. For a magnet, there are two poles. That is, there will always be a north and a south pole for a magnet. This particular charge particle in motion in a particular direction has magnetic and electric field. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we were discussing about what happens when its charge is in rest, what happens when it moves, and now we are going to discuss what are the other factors affecting when a charged particle is in motion. Yes, and that particular field is magnets. So, moving charges and magnetism. Here we will be discussing about the phenomena and theories regarding magnetism. So let's get right into it. So what exactly is a magnet? Where did the term magnet come from? All these are interesting questions. For this, we have to go back several centuries. It was actually in the 5th century that a person discovered, not a person, a group of people actually observed that, a community observed that certain rocks were sticking onto iron pieces and certain other metallic objects. And this was a fascinating phenomena, just like the case of amber sticking onto dry leaves. Here, rocks were sticking onto certain other metals. This was first observed in the 5th century. Later down the road, we saw that these rocks were more in concentration in a certain region known as Magnesia. And that particular region, Magnesia, is where the term magnet came into place. These rocks did have a higher concentration of ferrites or magnetites in them, which means that they had a magnetic property. So that is where the name actually came from. And later down the road, several scientists again observed that these innate properties were developed by certain other materials. For example, there is a physicist named Hans Christian. When he was studying about electric currents, so obviously there is a current flow, that is, I current was flowing through the circuit, and he accidentally kept a compass near that particular circuit. He saw that whenever there was a current flow inside this particular circuit, the compass needle deflected. You know what exactly a compass is, right? A compass will tell you the north and south directions. So, a compass will point north and south. So, normally this compass will be aligned to the Earth's magnetic pole. That is, Earth behaves like it has a big magnet inside that. So, the magnet will point towards the magnetic south of this particular Earth. That is, if this is the magnet near here, then here it will be south and here it will be north. It will be like that. So, naturally, a compass will always point towards the magnetic south of the Earth. That is, the compass north needle will be pointing towards the magnetic south of the Earth. So, when it was kept near a current carrying conductor, Hans Christian saw that the needle deflected, and he observed and tried to find out what causes that particular compass needle to deflect. Only another magnetic field can influence that particular deflection. So, why was it being generated? From there, a series of experiments and other observations were done, and finally certain other scientists such as Faraday, Tesla, everyone contributed, and finally it was Maxwell who unified everything together and gave us all the equations of magnetism that we have today. That is a grand unified equations for magnetism, and that is what we are going to study throughout this chapter. So let's get into the basics and let's start the chapter. Some of the basic things you need to understand before we get into this particular chapter is that the magnetic fields are generally represented like this, or like this. That is, we represent the magnetic field using dots or crosses. Why dots or crosses? This is where the name you have heard all the time, that is vectors. So vectors are the factor which indicates these two distinctive looks for a magnetic field. So this particular X or crosses means that the magnetic field is penetrating into the field of the paper, and this particular dots mean that the magnetic field is coming out of the paper. Now why is it so? It is because when we say a vector field, in this particular case a magnetic vector field, we can say that a magnetic vector field, vector B, is denoted as a vector. This particular piece right here is known as a vector arrow, which indicates direction, which means that this actually was an arrow. So this will be an arrow, right? The arrow we shoot from a bow. So that particular arrow will have a fletch. That is, the feathered part at the end of the arrow is known as a fletch. You can call it as a tail or whatever you want, and it'll have an arrow head. So imagine that somebody is shooting an arrow right at you. Then what will you see? You will see the pointed tip coming towards you, which means that you'll only see the tip coming towards you. That is this particular dot. So when the arrow is coming at you, that means the field is coming out. The field is coming out towards you. And if this particular cross is the one which is representing the field, which means that the arrow is going into the plane of the field. That is, it is going through the paper. You're only seeing the arrow going in. That is why it is an X shape, because this fletch will look like an X or into mark going into the field when the arrow is moving away from you. Here the arrow is coming towards you. That is why this cross and these dots exist. When there is a cross, it means the field lines is going into the paper, and this dot means the field lines are coming out of the plane of the paper. So direction is very important, and magnetic field is a vector quantity. That is why we use crosses and dots. And one more thing you might have already noticed, we indicate magnetic field in terms of the capital letter B. So capital letter B indicates magnetic field. Now, what about magnetic force? Just like electric field exerts an electric force, here magnetic field will exert a magnetic force. So how will that be? And what all will be affecting that particular magnetic field? For example, we can say that F is equal to QE. This was for an electrically charged particle. That is, we saw this for electrons or positive ions, positive charges and negative charges in general. So this particular equation is for an electrical force. That is, this particular force is electrical force, which represents the force by the electric field. Now, what will be the force experienced in a magnetic field? Will it be same? Will it be like F is equal to QB? Will it be magnetic field? Let's say FB is magnetic. So, will FB is equal to QB? It would have been the case if just like charges, monopoles existed for magnetic fields. Theoretically, they exist. Just a side entry apart from everything. Your NCERT says that there is no monopoles existing in nature. But actually, Maxwell's equations and other theoreticians have theorized that there is existence of a particle known as magnetic monopoles. It is theoretically possible. In principle, it is possible. But practically, we are unable to find it. So, if you ever manage to find it, there's a Nobel Prize waiting for you. Anyways, so if we could find monopoles existing, then we could have written this equation as QB. But there is no monopoles existing, which means that always for a magnet, there are two poles. That is, there will always be a north and a south pole for a magnet in practice, because theoretically monopoles do exist, but we are unable to find them. For that particular reason, we cannot write this particular equation like this, because here we can only say about positive charges or negative charges. But in the case of magnetic forces we cannot say just in terms of North Pole, just in terms of South Pole, because they do not exist. They actually do, but for now you assume that they do not. So we cannot write it as such. Now the second point is, where does this force arise from? So we know that Hans Christian observed when he placed a magnetic needle, that is a compass, near a current carrying conductor, it experienced a deflection, which means the current carrying conductor was producing its own magnetic field, which means that a moving charged particle, in that particular case it was the electron that was producing the magnetic field. So we can say that the moving charge is the factor that is producing the magnetic field. So what all factors will be affecting here? So when a charge is moving, obviously there is a charge q. So that is one factor. Now it will be moving with a velocity vector v. So how fast it is going and what is the magnitude of the charge, both of that factors matter. And these both play a vital role in developing the magnetic field. So what will be the force experienced for a charged particle when it is entering into a uniform magnetic field? We can say that that particular force will be directly proportional to the velocity of that particular particle. That particular force will be directly proportional to the magnitude of that particular charged particle. What charge it is it negative, is it positive? It is very sign sensitive. That will influence the force. It can be negative if the charged particle is negative. If it is positive, then the charged particle will also be positive. So is it F is equal to QV? No. When a charged particle is entering into, let's say, a uniform magnetic field, then these X's I just told you are uniform magnetic field lines which are going into the plane of the paper. So there is a magnetic field also, which means the force experienced here, will depend upon the strength of the magnetic field, capital B, the velocity of the particle, and the magnitude of that particular charge, which means that there are three components. And since these are vectorial properties, we will be adding them vectorially also, which means that the particular magnetic field experienced will be equal to charge times velocity cross this particular magnetic field. That is how we get the force experienced by a charged particle in a magnetic field going with a velocity v. So F is equal to Q into V cross B, that is vector V cross vector B. Both has directions. Velocity has a particular direction and the magnetic field also has a particular direction. So F is equal to Q into V cross B. Don't forget, the electric field was, let's say, EL, FEL was equal to Q times E. But here the magnetic field is equal to Q into V cross B. Lorentz was the scientist who studied more on this force aspects. We can also say forces in terms of Lorentz force, or we can just say it as F magnetic and F electric. And since it is a charged particle moving, we know that if we keep just a charged particle like this, there will be an electric field around that particular particle. Now what happens when that charged particle suddenly moves with a velocity v? Then instantaneously it also develops a magnetic field, which means that this particular charged particle in motion in a particular direction has magnetic and electric field. And we know that since these two forces are existing together, they add up together. The net force will be the sum of F electric plus F magnetic. That is, the net force on that particular charged particle moving in vacuum will be equal to, that is, F net. We can also say it as FL, that is Lorentz force, because Lorentz was the scientist who was studying on this particular phenomena. So we can also call them as Lorentz force. So we can say FL or F total or F net is equal to F electric plus F magnetic. it can be represented like this, which means that F electric and F magnetic together will be equal to Q into Q is common, so you can take the Q outside, plus it is electric plus magnetic, so E plus V cross B. So this is the equation to find out what is the net force experienced by a charged particle in motion in a uniform magnetic field. That is the Lorentz force, because that is also known as the Lorentz force, because Lorentz was the scientist who was examining all these and he made some discoveries and he clubbed all this together. Maxwell was the one who contributed and gave a unified theory for this, but still we call this as Lorentz force or total force experienced by a charged particle in motion, that is F electric plus F magnetic. So you can also remember Lorentz force. Don't forget about this. So that was the introduction, and we now know that the magnetic force experienced is equal to, that is FB is equal to V cross B into Q, or simply we can say that it is QVB sine theta. And this particular sine theta is because it is the cross product. It is the cross product between vector V and vector B. So that is why the sine theta is existing there. So we can just say that this particular sine theta or theta is the angle. Theta is the angle between V and B. So when a charged particle is moving through a magnetic field, the angle at which it is moving with a velocity. So the velocity vector V makes an angle with the magnetic field. That is, if let's say this is the magnetic field, which means the field lines are going inwards. And if the charged particle is going like this, the charged particle is being shot like this, then the velocity vector will be in this particular direction. But the magnetic field vector will be perpendicular to this particular velocity vector because it is going into the field while the velocity is at 90 degrees to that particular magnetic field. So angle does matter, and that particular angle is the angle between V and B, and that is indicated through sine theta because it is a cross product. So if the angle is 90 degrees, we can just say that it is QVB, which means F magnetic will be maximum when the velocity vector and the magnetic vectors are at 90 degree angles to each other. Then we can say that F magnetic will be at its maximum. If the velocity vector and the magnetic vector are parallel or anti-parallel to each other, that is, the angle theta is equal to 0 degrees. So if this is the direction of the magnetic field and the particular charged particle is going inwards with a velocity of V, we can say that both the directions are pointing at the same way, which means that the angle between those two lines are 0, that they are parallel lines. The angle between them is 0 degrees, which means that this particular quantity is 0. That is, sine theta will be 0, FB will be equal to 0 as sine 0 is 0. So there are two possibilities. When the angle between V and B is 90 degrees, you will get maximum force. If the angle between V and B is 0 degrees or parallel or anti-parallel, the entry is anti-parallel or parallel, you will get minimum force experience, that is 0 force experienced. One more thing you need to remember is that electric field and magnetic field are similar like in a lot of ways but different in other ways. Since magnetic field is a vector property or vector field, we can say that the vector fields add them together vectorially. Just like we use the principle of superposition for force, we can also use that vector addition for calculating the net magnetic field also. Just remember that magnetic fields add up vectorially. you also need to know some special rules regarding magnetism, and one of those first rules are right hand screw rule. It is also known as the cork screw rule, because it is like if you have a corkscrew, that is, if you have a screw which turns to its right hand side, then you can see that if I am holding the screw and I am tightening it, it goes inside. That is, as I turn it to the right hand side, it goes inside, and if I turn it to the left hand side, it comes right out. So that is known as right hand corkscrew rule, or that is called corkscrew rule, or simply right hand rule. So what right hand rule does is that if you know the direction of the current, then you can predict the direction of the magnetic field. That is, if imagine that you are holding a current carrying conductor, you have a wire which is carrying a current, or you know the direction of the current in that particular conductor. Imagine that you are holding that. If you are holding that particular current carrying conductor in your hand like this, and if you push out your thumb in the direction of the electric current, that is, if this is the direction of the electric current, then the curls of your finger, remember, the curls of your finger will give you the direction of the magnetic field. This will give you the direction of the magnetic field. So what will be the, if current is going up, I can say this is the direction of current and this will be the direction of magnetic field, or this curl will be the direction of magnetic field. Remember, for a wire which is carrying current, the magnetic field will be in circular shape. Why that is, we'll learn very shortly, but remember, for a wire that is carrying current, the magnetic field will be circular in shape. So this is how you find out the direction of magnetic field or electric current. If you know one of these two, you can find the other one. So that is known as right hand screw rule. One more rule is there for you to by heart, that is known as the left hand rule. People confuse right hand rule and left hand rule very often, so that is why I am discussing both these rules at the beginning of the chapter itself. So what exactly is left hand rule? So left hand rule gives you the force also acting. That is, the right hand rule gives you the direction of electric current and magnetic field, but the left hand rule gives you the force also. So imagine that your left hand is stretched out like this, and you fold and make a fist, so that this particular thumb is raised up and these two fingers are perpendicular to each other. That is, this is the x-axis, this is the y-axis, and this is the z-axis. All these three fingers are perpendicular to each other, which means the index finger is pointing at you, the thumb is pointing upwards, and the middle finger is pointing to the right side. So all these are perpendicular to each other, which means that these are x, y, and z axes. It is said that the left hand rule will give you, the thumb will indicate the direction of the force and the index finger will indicate the direction of the magnetic field, and finally the middle finger will indicate the direction of electric current. One more easier way to remember that is that, let's take the household example. In your house, who has the most boys? Generally in my house, it's my dad. So I can say that father has the higher authority. This is just for remembering purpose. Don't take it as anything offensive. So father has the higher authority. And next in line is my mom. So my mother will be the next person in command. And then only me and my brother, that is the children, comes into play. So then only the children's words are considered, which means that this is the order of the hierarchy. So we can just say that if these three fingers are these three persons in your household, you can say that this is the father, this is the mother, and this is the child, which means that this indicates force, the direction of force, and the next one, which is mother, indicates magnetic field. And finally, the third one, children, will indicate electric current. So remember, if, father, mother, children, which means that F is for force, M is for magnetic field, and C is for current. That is father, mother, child. All will be perpendicular to each other. Okay. So just to sum up, we learned about what is magnetic force and electric force. Together they are known as Lorentz force, and we also saw the equation to find out that particular thing. And one more thing you have to remember is that you know that you already studied that magnetic lines always start from the North Pole and end in the South Pole. But your textbook doesn't clearly explain this. So what actually happens is that for a moving charge, let's say this is a moving charge moving at a velocity v, it produces a magnetic field. This particular magnetic field produced does not essentially have a north and south pole, because the magnetic field around this particle will be in a circular shape. That is why when we use the right hand rule, it is a curl. It is a curl indicating the direction of the magnetic field. If this particular line element, the charge is moving like this, and this particular line element will produce a magnetic field which is circular in shape. If this was a wire carrying current, let's say I, then the magnetic field will be in circular shape, because according to right hand rule, if it is below, then we can say the magnetic field will be flipped in the other direction. Remember, the equations for magnetostatics or magnetism is highly sign sensitive. So if you flip the directions, everything will flip. So just remember that. The only way that a current carrying conductor has a north pole and a south pole is that that particular current carrying conductor is a closed loop. If current is running inside a closed loop, then automatically the magnetic field developed will behave like north pole and south pole. Unless that is the fact, then the circular shape will retain. One more side note is that in a magnetic field, no work is done in order to move a particle. That is because we saw that FB is equal to QVB, or it is equal to Q into V cross B. Right. So if this particular force and this particular velocity are at right angles to each other, what does that actually mean? It means that when a charged particle is moving with the velocity v, force will be perpendicular to the magnetic field, which means that these two are perpendicular to each other. The angle between them is 90 degrees, which again means the displacement and force are at an angle of 90 degrees. And the definition for work, W is equal to Fs cos theta, where S is displacement and cos 90 is 0. So if F and V are perpendicular to each other, then there is no work done. So in order to move a charged particle through a magnetic field, there is no work required, because the angle between the force and the velocity vector will be 90 degrees, and because of that, no work is basically done. And one more thing is that this particular magnetic field has the unit, that is the SI unit of, so Tesla is the SI unit of magnetic field. It is to honor a great scientist, Nikola Tesla. So we give the magnetic field its unit as Tesla. If you have any doubt why the force is perpendicular to the velocity vector, it will be all cleared in the next class when we discuss the motion of a charged particle around a uniform magnetic field. I hope you have understood the basic necessities that is required to understand magnetism and moving charges. So in the next class, we will study more about magnetism and its properties and certain other equations that is basically essential for you to understand magnetism. Thank you.